Yeah, I mean, I did. I didn't know what I wanted to do, and then I searched for the articles, and I was like, what? That's what I used to. What Franklin did.
Last night I
Okay, we've got 8:30. Why don't we get started? Good morning, Psych Stats.
Good morning.
Welcome to the last Wednesday of the semester. Looking forward to today's session where we're going to be talking about discriminant analysis. But before we get that far, I just wanted to give you a reminder that we'll be having our final exam this coming Monday, which will be at 9 a.m. here. And the final exam will be cumulative, as indicated in the syllabus. It'll be worth 100 points, which might sound like a lot, but that's only 10% of this grade. Remember, that's 10% of the grade that is 1/32 of your overall GPA. That won't matter when you're 25 years old. So we'll keep that all into perspective. The final exam will be mostly short answer. There might be some computation on it, but I'm going to try to minimize the total amount, at least of extended computations. Do you remember that early on you were doing some basic ratios, and you had to spend quite a bit of time inside of Excel computing all those? I'm not going to have that on there. You might need to use Excel to compute a few quantities, but I'm not sure I'm even going to have you save anything in Excel, or maybe not even in SPSS. So it's going to be largely conceptual rather than computational. And so TED-Ed will be your friend. You'll have, these will be, in some cases, maybe a direct TED-Ed question. There might be a spin on a TED-Ed question. But there might be some way to integrate some of the articles that we read, but I won't try to trip you up on a factoid from article number 7, experiment number 2. That's not what it's about. It's really going to be focusing on more the larger ideas and whether you can apply them to solve a particular problem in a short answer kind of scenario. Okay? So we'll say a little bit more about that on Friday, but that gives you some idea. Again, worth 100 points out of the 1,000 for the semester, and the entire course is only 1/32 of your GPA. All right. So what I'd like to do today is see if we can get into our conversation on discriminant analysis. So this was a TED-Ed that we had, and there were lots of great responses that I had seen in TED-Ed. So thank you to all those who had responded last night. Why don't we start out with having you help us out, and you have a copy of that here. We're also going to do a discriminant analysis in SPSS, and it's a little bit confusing given all the boxes that we have to click. They actually generate maybe more output, considerably more output than what we need, but we'll see if we can make some sense of the output today. So we'll just start out by understanding this conceptually before we try to grapple with the computation in SPSS. So in your own words, explain what discriminant analysis is. We'll give you a moment to call up your own response in TED-Ed if you want. Okay, thanks, Gabby.
Discriminant analysis determines whether two or more independent groups are separated from each other based on linear combinations, and then it also finds out which variables contribute to that. Okay,
so two things there. We were trying to somehow put participants or observations into two or more groups, right? And we're going to see if we can classify. So it's a classification procedure is one way of thinking about this. We're going to try to classify folks. We're not saying something is greater than something else, which is what we've been doing most of the semester, or something is correlated with something else. What we're saying instead is that this observation belongs in this category, this observation belongs in that category. There can be any number of categories. The minimum case would be 2. It turns out that if we think about the independent variables now as classifiers, right? Some of the classifiers are going to be maybe more instructive than others. They're going to provide more information. In my S&P class, I provide a definition of information, and we may have provided that definition here. Can somebody help us out with how we define information?
The reduction of uncertainty.
The reduction of uncertainty, okay? So here comes a particular observation, and we want to classify it, okay? Now, maybe we're told that we can put it into this category or into that category, and we're going to classify it, and we might have some information. We might be able to reduce the uncertainty about which category this observation belongs in, and some of the independent variables will reduce more uncertainty than will other variables. So it might be the case that we can say some variables are more informative, okay? And we might put heavier weight on the ones that are more informative. So which variables are helping us with this classification problem? And to set the stage a little bit more broadly, as psychologists, we can use this in lots of different ways. This has many applications. For those of you who might have clinical aspirations, you'll frequently want to understand whether your client should be classified this way or this way on a particular aspect of the DSM, right? Okay, so we can think about this as having many practical applications in psychology or beyond. Classification is a type of problem that all-purpose problem solvers like you will have to solve, and discriminant analysis can help us get there. Let's take a specific example. We'll go with the example of a sports psychologist, and we'll see how discriminant analysis can be used here. We'll see if we can come up with 5 predictor variables. Anybody want to share how they wanted to classify people and what their predictor variables were? Given that you're a sports psychologist. Okay, thanks, Hannah.
I said you could use it to predict which college athletes will succeed at the professional level.
Okay.
And I based that on height, weight, number of injuries, position, and number of points scored.
Okay, I'm going to get some of those down. Height, weight, the third one was number of injuries. Okay, so that's going to be inversely related, right? Some of these are going to be positively predicted. Generally, well, for lots of sports, height and weight, those are probably going to be higher for certain kinds of sports. I think if you're a jockey, it's probably lower, okay, so it might depend on the sport, right? Number of injuries, what were the other two?
Like position and number of points scored.
Okay, right. So, if it's points scored, it's probably not going to be a jockey. I actually don't know how jockeys are rated, but I'm not aware that they score points. Position might be something like, if you're a baseball player, if you're trying to predict that, is this shortstop versus, okay, that's not a rank ordering, right? That's okay, that particular position on a team, assuming a team sport, right? Okay. All right, so that works. And it might turn out that if we're trying to predict who is going to go on to professional softball or professional baseball, right? Some of these might predict more than others, right? It might turn out that this set really doesn't have a lot of predictive validity. Interestingly, it might turn out that this set has tremendous predictive validity, but not in a linear case. We're doing a linear discriminant analysis, right? But you can imagine that there could be highly ordered, highly non-random patterns that you and I could determine, but they wouldn't be linear. So for today, we're going to just motivate the conversation using, as Gabby said a moment ago, linear combinations of these. Okay, and that, I think, brings us to the next item. Anybody else have something they wanted to share before we go on to the next one, a sports psychologist that you were really jazzed about? Okay, all right. So one can use multiple linear discriminant analysis to sort scores on separate orthogonal dimensions of variability. For each of the 5 orthogonal dimensions in the 5-factor model of personality, generate 3 measurable variables that plausibly could be used in a linear discriminant analysis. Your response will contain 15 measured variables. Let's take some of these and see how we do. Okay, I'll put up ocean up here. And I just want to see how people thought about this. So in our 5-factor model of personality, the O stands for openness. Okay, so we're all on board with it. Anybody want to suggest 3 possible variables that could predict that you're going to be higher or lower on openness? Okay, thanks.
I have whether the person had lived in another country.
Okay, other country?
Whether they were involved in art, and whether they liked roller
coasters. Okay, now that's interesting. Okay, so this openness to new experience, some people are more inclined to travel, right? Others are less inclined to travel. Whether you like art, and maybe the type of art. You know, some art is, to use an informal expression, really out there, and people who might be open to novelty would like particularly cutting-edge art, perhaps. Others, if they like art, they might have preference for that which is very familiar. Right, okay, but okay, that could be a predictor. The roller coaster thing is interesting. So the idea here is that if you like roller coasters, you're more open. Is that okay? Okay, that might be right. It might turn out to be the case. I'm thinking of another variable. This might be predictive of what we might call sensation seeking. Right. Okay, and I might have thought that that would be best down here, right, for extroversion. They might be inclined. One idea about extroversion is people have a relatively low level of baseline arousal, and they seek the environment to really get them going, right? So they're looking for sensational experiences from their environment. So anyway, okay, that could be it. Just, I won't write them down. Does anybody have 3 others that they wanted to use for openness? Wanted to hear what people generated on openness. 3 other measured variables that might be used in a linear discriminant analysis to help us with openness. Okay, thanks, Jay.
Here's my 3 words: interest in abstract ideas, willingness to try new activities, and variability of past experiences.
Variability of past experience is a really cool way of thinking about it. If we think that past behavior predicts future behavior, right? Okay, so you get some idea of how exploratory they are. Okay, let's go to conscientiousness. We'll see if we can get somebody else to give us some predictors of conscientiousness. Anyone? 3 measurable variables that might help us figure out who's high or low on conscientiousness. Okay, thanks, Victoria.
They have a schedule.
Okay.
Take responsibility for their actions and follow through on commitments.
Take responsibility. And they follow through. Okay, I think that works. Okay, why don't we do extroversion? And maybe we don't need to do agreeableness and eroticism, but just to get a couple of more examples. Extroversion? Somebody want to help us out with that? Some predictor variables. We've already talked a little bit about roller coasters might be sensation seeking. Something else? Okay, thanks, Anna.
I had number of friends, words spoken per day, and then just general comfort around others.
Words spoken per day is really interesting. And comfort around others, is that what that was? Mm-hmm. Okay. And generally speaking, the more comfortable they are around others, the more extroverted they are. Okay, so that one's positively valenced. That one's positively valenced. Okay, so all 3 of those are positively valenced. Okay? They wouldn't have to be that way. You could find something that's highly predictive that's negatively balanced. Okay, I think we get the notion. We won't have to do agreeableness and neuroticism. I think we get the notion. We do want to reserve some time for going through the SPSS. Okay, so that was the 5-factor model. How does parsimony pertain to discriminant analysis? Okay, thanks, Melanie.
So discriminant analysis is used to determine whether or not there's a smaller subset of predictors that effectively explain the differences between groups.
Okay.
And since Occam's razor essentially says that the simplest explanation is best, if there's a smaller subset of predictors that can explain the differences between groups as what, in the same way that the larger set of predictors can, then the smaller subset is more parsimonious.
Okay, right. So thank you for invoking Occam's razor, and that again was all other things equal, the simplest explanation is the best. There might be a small set of predictors that really help us classify somebody along these dimensions or help us predict who's going to be the professional softball player, the professional baseball player. But maybe we don't need a lot of variables to get there. We can think about which ones are giving us the most information, which ones are reducing the most uncertainty. And the constraint there is, of course, that we're using a linear model in this case. Right? We're going to be using a linear model as opposed to a nonlinear model. Okay. So these are interesting. We'll go to questions 6 and 7 where we get some comparisons. Can we have somebody compare and contrast linear discriminant analysis with the ANOVA family of analyses? And what I meant by that, it might not have been obvious, the ANOVAs, the ANCOVAs, the MANOVAs and MANCOVAs, but just thinking broadly about ANOVA, how is it similar and maybe how is it different? Okay, thanks, Hannah.
I said that they're similar because they both are linear
Okay,
models.
they're both linear. Mhm.
They're based on means,
Uh-huh.
and they can be univariate or multivariate.
Okay. Mhm.
And then I said they're different because ANOVAs compared groups that you established beforehand.
Okay.
And linear discriminant analysis helps to determine those groups. Like helps determine groupings between variables.
Okay, all right, so lots of similarities there, lots of at least one important difference. Let's go back to some of those similarities, and we'll see this in the output when we're doing SPSS in just a moment. Let's say that you have some different predictor variables, and that you have, let's say, number of friends. Let's say we're trying to predict extroversion here, so we'll go with this number of friends. And let's say that we have some people that we know have been classified. I'll use this row as my introverts. I'll use that row as my extroverts. Okay, so here's introverts, extroverts. And let's say that we take a mean number of friends for this group of introverts, okay, and a mean number of friends for that group of extroverts. And it turns out that those means are absolutely identical. Okay? Those means are absolutely identical. So what we're going to find out is that we can compare those means just as we would in an ANOVA. Right? We can see whether these two groups differ from each other on the number of friends. It's going to turn out that if we get a non-significant ANOVA, then that particular variable probably is not going to have any predictive validity for our linear discriminant analysis. It's not going to help us in any way determine, right, what is predicting who's going to be an extrovert, who's not going to be an extrovert. Right? Okay, we need some mean difference there. Right? And if we don't have a mean difference, then that one's probably not going to be helping us out. Okay? How many people are following that? Is that working? Okay. Now, on the other hand, let's just say that the introverts had way fewer friends, okay, than did the extroverts. All right. Now, then if we look at the ANOVA there, the introverts would be way down here in number of friends, the extroverts would be way up here. There's a huge signal there, right? There's going to be a huge ANOVA difference. And so now we can begin to use that really large signal as a classifier. It wouldn't necessarily be perfect all the time, but it would be a statistical indicator that we could use this. We can go from here to here, right, with some level of, some greater than chance level of predictive power. Okay, so we'll see in the output from the discriminant analysis that we might want to take a peek at the ANOVAs. Okay, so that's how they're similar. They're both linear. We can do this in a multivariate manner. We can do this in a univariate manner. Today we're going to be doing it in a univariate manner, but you could extend it to the multivariate case. Okay, then there's this other very interesting point of contrast, and that is in the example that I gave just a moment ago, we know that these are the introverts. We know that those are the extroverts. So we're going to be using the group as the independent variable, right? And we're going to try to predict, maybe the number of friends, or we're at least going to compare the means on the number of friends. We're almost spinning the whole thing around. We're inverting what is DV and what is IV in the linear discriminant analysis. We're just flipping those two around, and we're going to try to develop a model so that we can begin to predict future cases. Okay, and I think maybe I've already answered one of the questions that's coming up. But let's go ahead to question number 7, and we'll see if somebody can say in their own words how they've compared and contrasted linear discriminant analysis with factor analysis. Okay, thanks, Victoria.
So both linear discriminant analysis and factor analysis the linear combination of the variables.
Okay.
However, in factor analysis, the groups are kind of interdependent, while in linear discriminant analysis, they actually make a distinction between IVs and DVs.
Okay. Okay. Yep. We're going to very definitely say which one is the IV and which one is the DV. We're trying to predict group membership, right? That's the idea here in linear discriminant analysis. So we're trying to predict group membership, and we're really not saying that we're using one to predict the other in factor analysis. That's how they're different, right? But there could be factors. There can be multiple measured variables, as we have here, and when we have multiple measured variables, it looks like we're referring to building up toward a uber variable or a latent variable, right? So all of these are ways of indexing extroversion. All of these are ways of indexing conscientiousness. We don't directly observe conscientiousness, but we infer conscientiousness based on clusters of measured variables, okay? So they both have that going for them, okay? But in the case of the linear discriminant analysis, we have a very clear IV and a very clear DV, and the DV is going to be some kind of group membership. Who's okay with that? That working for us? Okay. Okay, let's go on to number 8. In your own words, explain why linear discriminant analysis requires a data set for which participants' group membership is already known. I kind of went over that a moment ago. Can somebody just state that in their own words? Why do we require a data set for which each participant's group membership is already known? Thanks, Gabby.
We're trying to make a model to predict future cases whose group membership is not known.
Yeah, that's very much the case. Who remembers hearing about, maybe from Intro to Psych, the MMPI, right, the multiphasic personality, Minnesota multiphasic personality inventory? People remember hearing about that? So the idea there was very much related to this linear discriminant analysis, and that is, well, why don't we just take a whole bunch of patients from around the country that we know have been classified with depression or have been classified with obsessive compulsive disorder or post-traumatic stress disorder or schizophrenia, and why don't we look at what they all have in common, right? Okay? So we already have information on that particular group, right, or on all of those groups, and we'll see what kinds of things are predicting who's in what group. And then once we aggregate all that data and we try to find some patterns, then we know that in the years to come we're going to be encountering new patients, and maybe we can use existing diagnoses to help us with future diagnoses. We're building a model. Right? Who's okay with that? Yep. Because it might seem trivial, but people might say, well, why do we bother, answering this question if we already know what group the members are in? The question is, can we find a linear discriminator? Can we find a set of variables that we can combine linearly in such a way that we can predict future cases? Okay, let's develop a pictorial intuition. And I asked people to draw this, and so I just went to Draw 2 a little while ago, and I picked up 2 of yours, and I asked you to create a scheme, something like this. We drew a negatively sloped trend here, a linear trend, and then we can see that we have circles on one side, X's on the other, right? So what's interesting about this, I think sometimes a picture will say 1,000 words. This is really our linear discriminator. If you drew that line, you really would be discriminating the X's from the O's, okay? And here the word discriminate is to distinguish, right? We're not talking about discriminatory practices. We're talking about to discriminate X's from O's. And it wouldn't have to be the case that everything is linearly discriminable. But in this particular diagram, we get a really nice picture of what is linearly discriminable. I think I have another one too. Same kind of a thing. Okay? These big red O's down here, and here are the blue X's, nicely separated by that line. Okay? Now, where does that line come from? Well, that line comes from the combination of a bunch of measured predictor variables, and not just a combination, but the linear combination of those predictor variables. Okay? So we might get lucky. It might turn out that something that we're trying to predict, some group membership that we're interested in, actually is linearly discriminable based on known information. It won't always be that case, but it might turn out to be that case. Who's following that? In that question, I asked, I'll take a slight departure here, and this is something I haven't tried with it earlier. I've done linear discriminant analysis with my earlier classes in this this course, but I haven't done this next idea. So our y-axis contains what? Score. Our x-axis contains what? Something. Okay. That sneaky professor. What did the professor tell you to write on the x-axis in the question? Nothing. What would you have written? Everybody here is actually quite good at creating. I was really pleased with Draw 2 this semester. So you got that beautiful picture. This picture says 1,000 words. That is our linear discriminator, right? We left this one out for the minute. What would that say? How many people are not sure what it would say? Okay? How many people think they've got an idea what it would say? Okay, so I think we're not entirely sure. So this is why it gets a little bit tricky. So this is a line. Let's all yell out from 7th grade. What's our equation for a line? All right, we're all on that one, okay? So we know that there's a sense in which our y is our score, okay? We also have some intuition that this is the x, but what is the x, okay? Now, here's one way of thinking about it. We'll do just a little bit of practice this morning if you want to draw with me. Okay? And you're probably all better, I'm sure you're all better at drawing than I am, but we're just going to draw a little something. But to motivate that, I'm going to ask us to think about something that we might have learned in geometry class. So in geometry, way back in high school, who remembers hearing about a point? Right? There's like a point in space, right? Okay. Then we can extend the point into a line. Who remembers that? You can take a point and you can extend it into a line. Yeah? Okay. If I were to extend the line, what would it turn into? A plane, okay? So the point is, we might call that dimensionless, okay? The line is one-dimensional. I can go from here to here on this one dimension. The plane is two-dimensional. I can go from x up to y. So far, so good? If I were to take it one more time and extend it, what might the plane turn into? I start with the point. I expand the point by one dimension. It turns into a line. I extend the one-dimensional line into a two-dimensional plane. I extend the two-dimensional plane into a three-dimensional...
Space.
Okay, three-dimensional space. Okay, that actually works. Okay, this is a one-dimensional space. This is a two-dimensional space. We are each three-dimensional spaces. Okay, our bodies are three-dimensional. Okay, so if you're doing something like you're trying to come up with 3 predictor variables for extroversion, or 5 predictor variables for what makes a good athlete or professional athlete or something like that. Any one of those may have been along this one dimension, and here's the low end of that dimension, here's the high end of that dimension, and here's the mean, right? So we're still using means. ANOVAs are based on means, linear discriminant analyses, our parametric tests are based on means, okay? And so if we just have x and y, everybody's very comfortable. But what happens if we have now multiple dimensions? So here's where I'm going to ask you to draw with me. First, let's draw a line. Okay. Who's got the line? Okay. Can we turn the line into a surface or a plane that is approximately square? And I'm not good at drawing squares, but that's approximately square. It's okay if it's a little bit rectangular. Okay. So we've gone from one dimension to 2 dimensions. Who's okay with that? Yeah? Okay. Now what we're going to do is I'm going to try to have this go 3-dimensional. You're probably all better than I am at drawing 3-dimensional figures, but just in case, we're going to draw one more box, but we're going to place the box a little bit downward and to the right. So I'm going to draw a box of approximately the same size. Doesn't have to be perfectly the same size, but it helps if it is. Okay. So I have box and downward rightward shifted box. Okay. And I can already see that some of you are connecting the dots. I'm going to connect the upper left-hand portion of this to that. The lower left-hand portion, to that. I'm going to do this guy to this guy, this guy to this guy, and I bet that your box looks better than mine, but we've gone from a line to a surface to a cube in this case. 3-dimensional was how Gwen described it. That's fine. We'll call it a cube in this particular case. Who's all right with that? Yeah, did I lose anybody there? Okay. Right. So far we've got that much. So in this simple case, what most people do is we're trying to predict a score based on some other score. We're predicting one dimension over here based on one dimension. But suppose I were to do this. Here's my regular Cartesian plot like you've always had. I'm predicting this one by this one. But now, instead of just placing, let's say I'm going to try to predict whether Shelby is an extrovert or not. I'm going to take the first measured variable, which might be something like number of friends. That tells me how far she is over on this axis. And then what were some of the other ones for, was it talkativeness or number of words spoken per day? Okay. It might be that she's up this high or down that low on number of words. So now we're going to put her on a 2-dimensional plane, and then we're going to pull her out, okay, right, if you will, and whatever our third variable was, I think it was comfort with people, okay? So if she's very comfortable with people, she'll be way away from this board. If she's less comfortable from the people, she's going to be into the board, okay? So we can actually put Shelby in a 3-dimensional space, and we can linearly combine those things to come up with one score for Shelby on this, and maybe she's going to land above our discriminant line, maybe she's going to land below the discriminant line, but this is one of the ways of thinking about how we collect all these different dimensions of variability and use them to predict a particular score that we can try to linearly discriminate. Who's following that? Did that work for us? Okay? Right. So it's interesting to think about having one predictor, 2 predictors, that changes the x-axis, right? It changes the dimensionality. 3 predictors. If we get to 4 predictors, I'm out of dimensions. I'm not sure how to depict that spatially. But I do have a little trick that I think I'd offer to you. So from Intro to Psych, and certainly from S&P, but from Intro to Psych also, who remembers learning about rods and cones from Intro to Psych? And you learned about color vision. Does anybody remember that color itself has 3 dimensions? Okay, and what are those, if we remember what they are? 3 dimensions of color? Hue, saturation, brightness, okay? Maybe you talked about that in Intro to Psych, or maybe you didn't, okay? So now what you can imagine is that we're going to position Shelby in this 3-dimensional space. But we're also going to have a hue measurement, so to speak, on Shelby, and a brightness measurement, and a saturation measurement. So now we're going to picture Shelby as not only being a particular point in this 3-dimensional space, but she's going to be a particular color. And that color itself has 3 dimensions of variability. Who's okay with that? So now we can almost visualize 6 dimensions that go into predicting this one score. Okay? Then we can go to other features. We can go to something like, well, let's pretend that Shelby is not only this dot that's colored in a particular way in this 3-dimensional space, but it's also spinning in a particular direction, or at a particular speed. So now if you can imagine that ball is now colored in one way and it's rotating this way or spinning at this speed, now we have other ways of visualizing this. And the reason why I'm going through all of this is I want to let you know that one of the great challenges in solving difficult problems is how do we handle multivariable problems? How do we handle seeing and visualizing multivariate phenomena? And this is one of the ways of getting there, but spatially I can only draw these 3. Okay, but if you can imagine different colors, if you can imagine that it has different motions, you can imagine too that it has different sounds. Okay, there are ways in which trumpets differ from flutes, different from clarinets, different from violins. They differ in their timbre. They differ in their a tone can differ in its frequency or its loudness. So if you can imagine hearing that spinning ball that is colored and over here, now you're up to something like maybe 10 or 12 dimensions that you can somehow imagine. Okay. And so to be able to imagine 12 dimensions of variability while you're predicting one is a pretty handy thing to do. We're not going to try to do that here. I can't get into your imaginations, but I hope to have given you some way of thinking about this. Okay? All from this picture that says 1,000 words. Questions on any of that? Okay, let's go a little further. We're most of the way through, and then we'll do something in SPSS. Okay. So that was our picture. We're up to question number 10, and we'll see if we can have somebody explain the 3 assumptions that underlie the linear discriminant analysis. And maybe you can explain them to somebody less well-trained than yourself. So what are these assumptions? If it helps, are the same assumptions for an ANOVA. ANOVA's parametric, this is parametric. ANOVA's a linear model, this one's a linear model. Okay. The underlying assumptions? Can we just yell them out first if we don't want to explain them? Can we? So one of the assumptions is normalcy, okay, all right. Another assumption is equal variance, okay, and another assumption is independence. Okay, all right. Maybe we were on the ceiling in that one. People already have all 3 of those, okay. Bell-shaped curve, okay, equal variance. That's unequal, that's equal. Now the means are equal. Now the variances are unequal, right? So we've talked about that many times. The scores are independent of one another. So if Sarah assumes a score of 24 on a particular variable, that won't in any way preclude Gwen from assuming a 24 there, right? Those are entirely independent. So Sarah's score doesn't influence Gwen's score. Sarah's score on maybe one variable is independent of that on another variable that we're looking at. Okay. Logistic regression. Somebody help us out with what that is. And if you're really daring, how come that's question 11, given that we just talked about what we talked about in question 10? Maybe how this builds on question 10, but if not, that's okay. What is logistic regression? Okay, we'll get with Hannah and then with Melanie. Yeah.
It's a procedure that can help you predict membership into one of 2 groups.
Okay.
But you don't need the normalcy or equal variance assumption.
Okay, right. So we can now begin to predict into one of 2 groups. Okay, or you think of it this way: we can have it on this variable. The predictor variable itself can be nominal. The predictor variable can be categorical. Okay. So normally what we're doing is we're taking continuous variables over here, like number of friends, comfort level with other people, and so forth. That's continuous, and because it's continuous, we can take means. Okay. and we can take means that we can then find standard deviations on those means, and then we can see, is something a significant predictor or not using an ANOVA, right? But if we have just this categorical measure, then maybe we could use something like a chi-square, but we wouldn't be able to find a mean on a categorical measure. Okay? Who's all right with that? Is that working for us? Okay. And I think Hannah already alluded to it. If we have a violation of our assumptions, right? Maybe we have, for example, a highly skewed variable, then we probably wouldn't want to use a linear discriminant analysis, but we could still classify using logistic regression. Okay? But we wouldn't have to worry about the underlying assumptions. I think that gives us to the next question. Provide a specific novel example for which logistic regression would be more appropriate than would linear discriminant analysis, and why that might be the case. Anybody generate a novel example there? So one way of thinking about this is, can you think of a case where you would have a violation to your assumptions? Right? We just talked about what the 3 assumptions were. So if one of the assumptions were grossly violated, anybody have a specific novel example? Okay, Karen's got something.
I was looking at different groups of students and their level of stress over a semester, so I said it wouldn't fit within an assumption of normalcy because
Wow, okay.
it might be bimodal or...
Okay, that's really, really interesting. Where did I put my, here it is. Okay. Suppose we have a bimodal distribution of experienced stress. Okay, there it is, right? Okay, so that clearly is not normal. And if there's a strong departure from this and the normal curve, then maybe the stress is highly informative but happens to be non-normal. And so it doesn't really make sense to run an ANOVA on it if we're assuming normalcy. Remember that the ANOVAs are going to be assuming that a certain fraction falls below that line, a certain fraction falls above that line, because we know these properties of Gaussian curves. If you're departing tremendously from a Gaussian because it's multimodal, or perhaps because it's tremendously skewed off to one side, right, okay? And maybe the stress in a particular sample is tremendously skewed, then you might go with logistic regression. Okay, who's following that? That work? Okay. Sometimes you can just think of variables that might be tremendously skewed, and some might include such things as incomes. Right? There are very few people that make that much money. There are a lot of people who make that much money. Okay. Reaction times are often skewed this way. Okay. So those are some possibilities. Okay, logistic regression. We've already talked about comparing the means, so I do want to save some time for SPSS. Let's skip over number 13. As we said before, we had our introverts, we had our extroverts. If they have the same number of friends, then number of friends is not going to really help in the discriminant analysis. It's not going to tell us who's in one group, who's in the other. It doesn't provide any information. It doesn't reduce any uncertainty. Okay. I wonder if we can get to the Wilks lambda. How does that play a role in discriminant analysis? What do we know generally about Wilks lambda? Somebody help us out with that. We've come into that a few times, especially in the last couple of weeks. Wilks lambda does what for us? Okay, yeah, thanks.
The proportion of variance not explained.
Proportion variance not explained, okay, right? So as that's getting lower and lower and lower, our p-values will also be going down, right? Okay, so those are going to be covariant, okay? And then here's just one last one. I couldn't tell from people's responses this morning if people were understanding this. A few people said it's computed in SPSS, which I think we already know, but how is the accuracy of the LDA computed? It's actually quite simple. It's just a simple percent correct measure. Since we already know who's in which group, we know which persons are introverts, which persons are extroverts. We can say, what does our linear discriminator do for us? Does it classify 100% of the extroverts as such? 100% of the introverts as such? Did it make 1 error out of 20? Did it make 6 errors out of 20? If we have 100 cases and it got 94 of them right, then it's 94% correct. So we actually know what the expected value is. This is how it's similar to chi-square. We actually know that this person, this person, and this person are classified as being extroverted. These are introverted. And we can see what our predicted value is given our linear discriminator, and we can compare that predicted value to the expected value. Who's okay with that? But we're not going to difference those scores and square them as we would in a chi-square. We're just going to say what the percent correct was. Okay, so why don't we spend our remaining 10 minutes or so doing a linear discriminant analysis in SPSS. Okay, so if you'll open up SPSS, and I'll just point out where the new practice set is. We have the practice set that I developed in the PowerPoint, available out on the share drive. If we go to 370 in the resources, as always, and we'll go to the practice sets, there is one that's simply entitled Discriminant Analysis. And while you're calling that up, I'll project it up front, and I'll set the stage a little bit for what's going on here. Okay? So we're going to pretend that we are psychologists who are interested in the topic of recidivism, as we mentioned in the PowerPoint presentation. And what we want to know is whether somebody who is currently in jail is a repeat offender or not. Okay? Has this person who's in jail right now been incarcerated for other reasons previously? They were released and they came back in, versus folks who might be in jail as a first-timer, so to speak. Okay? And we might say, well, what might we use to predict that group membership, whether they are recidivist or not? So just by a show of hands, how many people are familiar with the concept of recidivism, these repeat offenders that we're looking for? Okay, so for a particular sample, either we have people who are repeating or not, and we're going to put them into groups 1 or 2. Okay, so that's our grouping variable. Kind of like we had introverts and extroverts a little while back, we have now a sample of 20, and I'm pretty sure that we've put in this hypothetical data set, 10 people are repeat offenders, 10 people are not. Okay? And the variables that we had a clue about that we thought might be helping us out would be their alcohol usage, their drug usage that's separate from alcohol, and their anger levels, the extent to which they're angry over a protracted period of time, or the quickness with which they become angry. Okay, and we can have some scale that goes up into the hundreds in measuring anger, and we have other kinds of scales here for measuring their drug usage and their alcohol usage. Okay, so we're going to use these as 3 predictor variables. Who's understanding the question at hand? Is that working for us? Right, we're trying to predict recidivism or not based on these 3 predictor variables. We'll use a linear discriminant analysis. Okay, all right. So does everybody have one of these? Okay, a moderately complicated set of clicks. If this is on the final exam, I will give you this. Okay. And in the interest of time, we're going to even use 1 click fewer than what's on here. So let's all do this together. First, just by a show of hands, how many people have the data set up? Okay. All right, that's really good. Let's go to Analyze, as always, something that we hadn't done before, but the way we started out today. This is a classification problem. Do we classify a particular observation as being a recidivist or not a recidivist? Okay, so we're going to go down to classify for the first time this semester. I am curious to see, has anybody used classification or the classify menu in any other class? Or a research, okay, so this is probably new for all of us. Lots of ways to classify. The one that interests us today is discriminate. So I'll let you click on that, and I'll just hold that path right there. Analyze, classify, discriminate. Okay, and we get this. Okay. Now what we want to do is we're going to have some grouping variable that very simply we call group. Okay. And we also have now 3 different predictor variables. So it's looking a little bit like this. You can imagine that we've got, on the one case, alcohol usage, drug usage, and then coming out this way, quick to anger. Right? Okay, so we're using this cube to predict a one-dimensional score that we might be able to linearly discriminate. Here we're above the line, here we're below the line. Okay, so let's grab those 3 all in one swoop. We'll slide them over. Okay, and then here, there's a lot of things to click on, so we're going to follow this pretty closely. We're up to number 6, and we're going to go to the statistics menu, and we want to take some means, and we'll also do a univariate ANOVA. We wouldn't have to look at those things, but I did want to give you an intuition about why these are all related. So we'll see how the means might differ from each other, how that relates to ANOVA, and when we get a non-significant difference in these different predictor variables, or these ensemble of predictor variables, we'll see if that's predictive or not for our linear discriminator. Okay, so that's all good. Why don't we take these 2? These also, I should say. So we'll take all 4 of those, and we may or may not use them. In fact, I'm sure we're going to not use some of them, but we'll just click on them to get that going for right now. Okay, so that was the statistics box. Let's now click on the classify box, and some things are given to us automatically here. Okay, we already get a prior probabilities. Within groups, we'll take that as well. I do say in number 10 that I'd like you to click on combined groups. We don't need to do that. Okay, we don't need to click on combined groups. But I would like to get a summary table. Okay. Is that working for us? People have all of that? Okay, so we're going to take the summary table and we'll click that down. Okay. Then we'll go to save. Okay. And for right now, why don't we just get the predicted group membership? Okay. Yeah, we'll leave it at that. I was going to say, it's fun to look at discriminant scores, but we have only a few minutes left. Okay. We also need to define our groups. I skipped over a step. I apologize for that. You can have any number of groups inside of your data set. You might have 12 different groups. You might have 5 different categories. But for right now, we're going to use only the 2 categories. So let's define our range. And we have group 1. These are the non-recidivists. These are the first-timers. Okay. And group 2 will be our repeat offenders. These are the 2-timers. They've been in jail at least 2 times or more. Okay. So we have groups 1 and 2. Okay. So we're going to try to classify our data into group 1 or 2 using these 3. Okay. These 3 predictor variables with all of those parameters that we saved. Okay. I'm going to click on our right or OK, and we'll let this come up. And many of these boxes we don't need, but let's see if we can take a look at the ones that are maybe most predictive. Okay, so let's go to the group statistics. I think this helps us. Okay. And let's take a look, for example, at alcohol. This is just a little bit busy. We have 2 groups, if you'll follow with me. We have the first-timers and the 2-timers, okay, groups 1 and 2, right? The non-recidivists and the recidivists. And if we take a peek at alcohol, we see that we do get a mean difference, that the mean alcohol usage, so to speak, or the score for alcohol, was 8.5 for group 1 and 11.1 for alcohol. So those means are not identical. We could potentially exploit that information to begin to classify future cases as recidivist or non-recidivist because there is a mean difference. Okay? If we go to drug, we have 9.2 versus 9.8. That's a difference. It's not a very large difference. Okay? So we might think of it this way. We don't have a very big signal between those means, right? So that's probably not going to be a real powerful predictor. Although in principle it could be if you had a really, really tiny error bar. Okay? Then that could be a good predictor, but otherwise probably not. And then we'll go to anger, and we have 212 versus 256. Okay, so that's a pretty good spread. We do have a pretty good sized standard deviation, but if we shrink that down by the standard error divided by square root of n, that might turn out to be really quite diagnostic of who's in which group. So just taking a peek at the means and the mean differences gives us some idea about what might be classifying and what's not so classifying. Okay? Who's following that? Yeah. Okay. Let's take a look at the next one down. We wouldn't have to, but we'll just take a peek at test of equality of group means, and we're getting the F values here, and correspondingly we're getting the Wilks lambda shown over on this side. And you can see that drug, as we suspected a moment ago, really doesn't have a significant F. Those means were quite similar to each other. By contrast, we're getting a big fat F and a associatedly lower Wilks lambda associated with anger. So the anger is quite predictive, and the alcohol is somewhat in between those two. Okay? Let's skip over the next couple. Okay, we'll come down here to the Wilks lambda for the entire model. Okay, and so 55% of the variation here is unaccounted for by our model. Okay, take a quick look at this one. It wasn't on the PowerPoint, but I think you might find this one to be interesting. Okay, we are going to be linearly combining these different variables, and these would be the coefficients had you z-transformed everything. Right, you would have a coefficient of 0.595. for alcohol, negative 0.559 for drug. And notice that the strongest coefficient, the one that has the heaviest weight, is anger. And hopefully that makes sense to you because that was the one that had the greatest mean difference when we looked at the ANOVA. Does that sound familiar? Yeah, okay. So you'd want to put the most weight on that one. It seems to have the greatest diagnosticity. Okay? All right, and then we'll drop down for our final conclusion, and we're all the way down this way, and we see that we have these classification results, that we actually did 80% correct, okay, on our classification, and we missed a couple of times. We missed 4 times, actually, in our set of 20. So we classified this better than chance. If we were just at chance, we would have had 50% correct classification, 50% incorrect, given that we have 2 possible outcomes, and they were equally distributed ahead of time. So we got from being 50% correct up to being 80% correct by using this linear discriminator. Who's following all that? Yeah? Okay. If we have time, when we come back next time, we'll take a look at the particular cases and see which ones missed and why. So it might have been the case that a recidivist had an unusually low score for a recidivist in anger, right? And that's why this was misclassified. Okay. For tomorrow, you've worked hard. Let's take the day off. Okay. You're not going to be in tomorrow, but I would like you to come in on Friday and answer the TED Ed that is available to you already out there. And this TED Ed is going to be a TED Ed that is going to be for a student-generated review session. So what I'm going to ask you to do in this TED Ed is not read anything new. I thought about all the major topics, or at least 15 major topics that we've addressed, and I'm going to ask you to generate a question that you might be using to test a hypothetical study buddy on factor analysis, or on multiple regression, or on the sphericity assumption. Okay? You'll jot that into your TED Ed, and then we'll come in on Friday, and we can be in this arrangement. We'll have you try to respond to each other's questions, okay? And that will be our way of reviewing for Monday's final exam, okay? So get some sleep tomorrow. If you really want to come in and talk about stats tomorrow, I'll be here at 8 o'clock anyway, but you're not expected to be here. Thanks for a great session. I'll see you Friday morning at 8:30.
At least maybe. Yeah, I'm going to try to write a couple more sentences. Well, then it's like, no, you can't talk about it. You can read the problem as well. It's not complex in that sense. It's just like, oh, what's the current state of this issue? This issue, and then it was like, and then talk about like like the pharmacokinetic stuff. Exactly.
Pardon me, Vanessa, I'm sorry.